So, we start with the concept of assortativity. Okay. So, assortativity is something where likes goes with likes. That was what we told, and then we had this, you may be remembering that we had this black, Hispanic, white others, black, Hispanic, white others, and accordingly we have shown a associative matrix, and also we first proposed how to calculate associativity. This is the formula which we showed, and then we showed that this formula had some problems and proposed a new formula. Okay. So, let us explain the new formula. So, TRE means actually the trace of EII. Okay. So, we can write it as summation of EII minus EI means this is QI and this is say Q dash I. So, QI, this is Q dash I, QI and into Q dash I by 1 minus QI into Q dash I. Huh? Yeah. So, this is what the formula is. This is what the formula is. So, what is exactly happening? So, I can write it as also AI, BI, anything, whichever you. So, summation of EII minus summation of AIBI 1 minus summation of AIBI, whatever you want. Okay, clear? So, now what is our constraint? Our constraint is that it should, if it is totally disassociative, then what should be the value? If totally disassociative, yeah, totally disassociative, then it should be 0. Okay. So, let us analyze this formula. Okay. Let us analyze this formula and see what happens. Okay. So, when it is totally disassociative, then what is it? So, row is independent of column. So, if you take this matrix again, then a independent matrix will have what if this is AI and this is BI, or take any point. Okay. Say this is Tij and this is AI and this is Bj. Then what is the test of independence? What is the test of independence in this match? Simple, Tij equal to AI into Bj. Okay, for each pair of I and j. Okay, for each pair of ij. Clear? So, now go back to this formula. If it is totally disassociative, okay, then EII becomes equal to AIBI. Okay, sure. So, then R becomes 0. Clear? And if it is totally associative, then what happens? EII, summation of EII what does summation of EII become? 1. Okay. Summation of EII becomes 1. So, R becomes 1 minus summation of AIBI by 1 minus AIBI. Okay. Agreed? That is 1. Okay. Clear? So, this is what you are finding, that it ranges from, if it is totally disassociative you get 0, if it is associative you get 1. Okay. And what are the two problems which we discussed last class? One is should be given equal weightage to equal occurrence. If I have occurred many times, I should get more weightage, and if I have occurred less times, I should get less weightage. So, since we are summing over EII, since we are again, let us see, since we are summing over EII, since we are summing over EII, so what happens? Each individual element will get its due weight. Okay. So, that problem is solved, and the second problem was symmetry. So, since we have taken AIBJ or AIBI, so we have considered both columns and rows. So, symmetry is also maintained. Okay. Okay. So, now so what are AI and BI? This is the row sum is AI and the column sum is BJ. Okay. Clear? Okay, very good. Okay. So, then I hope we know the concept of associativity now. So, what is the next question we should ask? That is associativity in networks. Okay. So, this is the next question, next natural question which comes. Okay. We want to find associativity in networks. No problem? Okay. So, what does associativity in networks mean? Can anybody suggest what does associativity in network mean? No, that is clustering coefficient. Means, yeah, sure, you can have a rich man's club. So, that means associativity may lead to more clusters, that is correct, but a little more, can you tell? Similar degree. So, it will be actually similarity in terms of degree. Okay. Okay. So, now let us go back to this old example of black, Hispanics, whites and others. Okay. So, if I want to build up a matrix like this for networks, okay, what will it be and how will it be different from this? Okay. What will it be and how will it be different from this? So, tell me what will it be? Can you tell? Any suggestion? Huh? No. What were the rows and can you tell me what are the rows and what are the columns? So, rows will be the degree, and the columns will be again a degree. And if it is not a directed graph, then it will be symmetric. If it is a directed graph, it will be exactly like this case. Okay. Okay. But there is one fundamental difference between the black Hispanic example and this example. Can you tell me what is the fundamental difference? No, you can have many so you can have many nodes with single degree, okay, and that is connected to many nodes with say 2 degree. So, this is connected, this has got connected. So, it is not one that is important, but something more is important. See, in the previous case what we saw, there was no relationship between the attributes. Here it was black, here it was Hispanic. So, is black more distance to Hispanics or white? We did not have any such measure, but a 1 degree node getting connected with a 2 degree node is more associative than a 1 degree node getting connected to say a 1000 degree node. So, here these values also have some meaning.
You are not taking into account how many friends one person has in that.
How many?
How many one person is linking to how many others in the previous black Hispanic example.
Yeah.
You are not, I think, not paying attention to how many one person is linking how many others.
No, in previous, so in the previous case, what was group membership? What were the sets? Let us think what were the sets. Sets are blacks, black men or black women, white men or white women. And here what are the sets? This set is nodes with degree 1. Okay. This set is nodes with degree 1, nodes with degree 2. So, same, it is similar type of sets. Okay.
That would be the case if a person, one black man is linked with more than one person. Here also it was on types of vertices.
Here also types of vertices. Yeah, so here is also types of vertices, that nodes, type of nodes with degree 1, the type of people with black colors, black skins color. So, it is same, but one important thing which will come is that if I am connected with a if a 1 degree node is connected with a 2 degree node, that is more associative than a 1 degree node connecting with a 5 degree node. Okay.
Then how do you describe a higher associativity in the black Hispanic example? Here you saying more associativity is when 1 degree node is connected to a multiple degree node.
No, more associativity is always if 1 degree node is connected with a 1 degree node and 10 degree node is connected with a 10 degree node. But what I am telling, a 1 degree node connected with 2 degree node is more associative than a 1 degree node connected with a 5 degree node. There is more similarity here, less, but a black women marrying a white men or a black women marrying a black woman marrying a Hispanic men are both similarly disassociative. So, we cannot talk about degree of associativity or degree of disassociativity in that case. Okay. I think things are clear. Okay. So, then what will happen? So, previous case what we were doing, think that we were just taking this EIIs. Okay. Previous case we were taking just this EIIs, and what was that? That this EII is basically how much independent is it or how much dependent is it was tested. Okay. Clear? Now, what you have to do? You have to take for all i's and for all j's, that EIJ is how how much is this value, that is important, okay, because you have to take it for all values. Okay. So, this way things can go on, and just to think what is I and what is J, I will mention one more concept which is important for networks perspective, not from associative perspective, is that you take these two nodes and you have a connection. Okay. So, you have a connection. So, and you have, so what are you mostly interested in? You are mostly interested in this distribution. Okay. You are interested in this distribution. So, this distribution is basically the main distribution minus 1. Okay. So, what we call is, what we call this is remaining degree. Okay. This is classically termed as remaining degree. So, when we are considering this E I j, so I is node with remaining degree I, okay, node with remaining degree j. Okay, things are clear. Okay. So, now with so taking all this I and j into consideration, you can go on doing some mathematics, and at the end for a particular network you get this formula. I will not go into the details of the formula, but you will get this formula, and we can intuitively see what this formula means. So, for all i's, so what you take is, see this, you are taking basically half of A I J I. So, you are taking J I K I, two nodes, one node has degree J I, another node has degree K I, and when we are some minusing, we are basically seeing that how much it differs from their mean. Okay. So, more disassociative it will be, the more it will differ from its mean. So, it is just similarly where m is actually total number of edges. Okay. Okay. So, the next question which we will ask is, or I will just say is degree distribution clear to everybody? Because this is needed for the next step. So, I again tell, so you have n nodes. Okay. So, nodes, I write degree and number of nodes. So, nodes with degree 1 say is n 1, nodes with degree 2 is n 2. Okay. So, this way it goes, and nodes with say degree n, or no, n is a bad choice, node with degree k is n k. Okay. So, what is N1? Let us tell it in words. What is N1, Orithro? Number of nodes having degree 1. Okay, no problem. So, now what we can do is that taking the same thing we can write degree probability. 1 is N1 by N, where N is actually summation of Ni's, okay, and this I can write as P1, 2 N2 by N, which is P2, okay. This way K Nk by N, which is Pk. So, can you say what is Pk? Jagan, can you tell what is Pk? Probability of a node having so it is little different from this. Here what was it? Number of nodes having degree 1 or number of having nodes degree k, whichever you want to say. Here is now you go to one node, probability that a node is having degree k. Clear? So, this is what is degree distribution. Okay, I hope it is clear. Okay. So, next is what is the importance of degree distribution? It is the easiest way to characterize a network, okay, or it is the most simplest way to characterize a network. So, what is the most simple network? Huh? No, okay, most simple random network, I should ask like that. How can we, if I am given n nodes, okay, n nodes, and I am told to construct a network randomly, network randomly, what will you do? Yeah, you uniform distribution, but how will you implement that?
Connect one with another, then pick up another one.
So, you have these nodes, you pick each pair, you can connect with probability p. So, that is the simplest way of thinking, that each pair you connect with probability. This is connected, this is connected, this does not get connected, this gets connected, this gets connected, and this gets connected, this and all the other pairs fail. Okay.
So like if we have a network that is, one node is connected with everyone and rest of the node having degree 1.
Yeah, that is a
Then
star.
That is a star network.
Yeah.
Then if we are finding probability distribution,
Yeah.
that then Pk for the central one, which is connected to everybody, having highest probability.
Yeah.
But if we are picking any node randomly,
Yeah.
then it is most probably that the degree will be 1. But from this distribution, what we are getting, that if we are
Great. So, that was the question. See, in a star network, what you are telling, in a star network, if only one node has high degree, all others have very low degree. But if I randomly pick up a node, it will be a low degree node. That is the idea behind the main concept, that internet is very robust to random failure, but very vulnerable to targeted attack. So, internet is some sort of star network. So, if you can somehow identify the middle, then you can immediately break it. But if you are a blind guy, every time you pick, you will pick something in the periphery. Okay. So, anyway, that we will come to these questions later, but the degree distribution is clear and construction, graph construction is clear. So, now the next question is, so this will most probably follow what you are telling uniform, or it will follow a Poisson distribution. If I see the degree distribution, you will see it will follow a Poisson distribution. Yeah, picking up random all possible pairs NC2, and for each I am collecting with a probability P. I am picking each pair, I am not leaving any pair, each pair I am picking, but I am connecting with probability P. Means in the end I will have this number of edges will be NC2P. Okay. Yeah, it can be. It is not that it will be a connected graph. No, that is not guaranteed, or we will see that what should be, these things we will see that what should be the value of P, so that it be it is a connected graph, the probability that it is a connected graph becomes very high. So, those things will be seen later. Anyway, so degree distribution will become Poisson. Okay. No, it is not 1 by NC2. Everybody will not have 1 by NC2. So, you can do, and you will see this is basically a Bernoulli's trial which you are doing. So, it will come to Poisson. But the next question which we ask is that Poisson, I do not want Poisson, I want scale free. Okay. I want degree distribution something like this. Okay. Say, or I want arbitrary degree distribution. I am supplied with P1, P2, okay, Pk. Say I am supplied with this degree distribution. Actually, it should be, if there are n nodes, what can be the highest? Pn minus 1. Okay. If there are n nodes, the highest degree, if n nodes. Okay. I am given this. I am given this. Okay. So, now I have to generate a graph. Okay. Question is clear, but it should be random enough. It is not that I can hand pick. I have to design a random algorithm. Okay. Problem is clear. Okay. So, what we can do from this given n, I can know these things. Okay. If I am given a probability distribution, and if I have given number of nodes, just reverse process of the previous thing, I can know n1 nk. Now, you put n nodes. Okay. So, this will be say n1 nodes. Means these are nodes with degree 1. These are nodes with degree 1. Then nodes with degree 2. Okay, this way you can go on. Now, for each, what you do? You randomly create stubs or ends. So, for this you create 1, for this is create 1, for this you create 2, 2, let this be 3. So, 3. Okay. First create stubs. So, step 1 is create stubs. Clear? Create stubs, and then what you do? Join these stubs randomly. Pick 2 stub and join randomly. Okay. So, take this stub and join this. Take this, join this. Take this, perhaps join this. Take this and perhaps join. So, let me think there are 3 here. So, then what you have the problem? No, I am just changing this. Let this be in the category of n3. Okay. I am changing this to identify the problem. Now, what is the problem here? that this node has 2 degrees left, which are and then it is forming a self loop. The last is forming a self loop. So that's why what you do typically algorithm wise, one you can discard this anomalies, small anomalies, okay, or you can backtrack a little. Clear? Okay. So, this is what is popularly called a configuration model. Okay. No, not the stubs, the links. In backtrack, what you do, you take out some established edges and then again rewire. Okay. You take out some established edges and then again rewire. Then connecting. So, this is what is called configuration model. Okay. Clear? Okay. So, now I again come back. Now, I again come back to the assortativity concept. So, what was our first thing in assortativity we saw? I think we saw this one, huh? Okay. This is what is assortative. Okay. And then what we saw is this one, this matrix. So, what is the question? The question is, from this matrix can we generate this network? Okay. From this matrix, so still now what we were doing? We were doing analysis. Now the synthesis question comes. Okay. That from this matrix can we generate this? Okay. Clear? Okay. So now let us think that our informations present in this matrix is enough, or we need some more further informations. Okay. So that we will try to find out step by step. Okay. So we have this E matrix. Okay. Again I come. We have this E matrix. Okay. And then if I am told that I given E matrix and given that you can have M edges. Okay. Given E matrix and given M edges. So, okay, I think I will take a say a more simpler example for this, then it's easy. Given E matrix, given M edges like 0.18, 0.02, 0.01, 0.03. Okay, This way things can go 0 0.20, 0.16, 0.22. Okay. And let us think. So, this is I, A, B, C, D, and this is also A, B, C, D. Clear? I am thinking symmetric. Okay. For the time being, to avoid problems, I am thinking symmetric. So, now and given M, so how many, say M is equal to 100. So, how many edges between A and A, type A and type A? So, 100 into 0.8, 18. Okay. Then how many between say A and B? 2. So, this is clear. So, now simply what we do, we begin to draw the edges. So, A, then A, B, this way goes, A, D, then I go this way, okay, B, B, okay. This way I can draw all the M edges. Okay, so I can have BA, then BB. Okay. Means if I think this will be actually 4, because I have to consider BA and AB both. Okay, because this is a E matrix and this is symmetric. So, BA and AB will have 4 both together. Okay. So, now this is there. So, from here you know number of edges A has. Okay. Now, means number of edges, A means group A. Okay. Number of edges group A has. Okay. No problem. Or number of edges group B has. Okay. Okay. Now, group A. So, group A actually will have some NA number of nodes. Group A will have NA number of nodes. Okay. Because this is what group A is. Okay. It will have NA number of nodes, but what is the value of NA? What is its value? Okay. So, this is the question I want to ask, that what is its value. So, this does not come from anywhere of the original data. Okay. Then what do? We say that group A follows a degree distribution. Group A follows a degree distribution. Okay. No problem. So, degree distribution which we can characterize as PK. So, what is the average number of nodes, average number of edges our degree distribution will have z, which is equal to sigma k p k. Okay. So, if we know this degree distribution, let us assume that we know this degree distribution. Okay. That we know this degree distribution, then we know z. So, this thing we have to know, and as soon as we know z, we know average z is the average degree distribution. K is nodes with degree k. So, k is the degree. So, nodes with degree 1, k p k is what? So, p k is the degree distribution and k p k gives the average degree. Think it is simple, it comes. Okay, it is the average degree. No, this is k p k. So, this is the average, not its summation. Summation, total number of edges is total number of edges what? How much? K n k, summation of k n k. Number of nodes with degree 1 into 1, number of plus number of nodes with degree 2 into 2, plus number of nodes with degree 3 into 3. Okay. And what has happened is basically 1 by n summation of k n k gives you the average, and that you have written as summation of k p k. Okay. I think this is clear. Okay. So, if you are given z or if you are given p k and then you find z and number of nodes, you know M A. From this, from the E matrix you know M A. So, now you know N A is equal to M A by Z. You know how many edges group A has, and you know the average degree of this group. So, you know how many nodes are there. So, now what do you have? You have okay. Any question? I think it's perfect. Okay. So, then where are we? We basically have groups NA, NB, NC, okay, and ND. I am just taking 4. So, inside each group what we have? Edges, nodes. Inside each group you have nodes, and what else do you know? Tell me. You know the degree distribution. So, what you can do immediately? You can build stubs. Okay. You can accordingly build stubs. For this also you can build stubs. This you build stub. Clear? Because you know the degree distribution, according to the configuration models you can build stubs. Clear? Okay. And then you know how many from here, again see here, you know how many will be connected to AA, how many between AB, how many between BA. Okay. So, what you have? You know AA, number of edges between AA, number of edges between A and say C, okay, number of edges between B and C. So, you know everything, clear. So, now what will you do? Simply for this number of times you will pick two nodes from A and join them. For this number of times you will pick one node from A and one node from C and join them, okay, and accordingly you will have the associative clustered, we will have the associative clustered network, okay.
So how the groups are made?
How the
Groups are made.
from the E matrix. E matrix has specified, and we have taken one more input, is that we know the degree distribution of each group.
Each group will have similar vertices, similar type of vertices.
No, some group may be Poisson, some group may be scale free, so we do not know, but
Type of vertices.
hey, it is a similar type of matrix.
Each group will have similar type of vertices.
Each group has similar type of, that is the assumption that each group has similar type of vertices. Okay. So, that is what I think somebody told in the beginning of the class, that associativity brings about community formation. So, this is exactly what is happening using associativity and building communities. Okay. So, in the end of this algorithm we can say using associativity and building community. This is what we have achieved. So, anyway, so we end the associativity concept here. I will just end by showing you this. This picture. So, what you see? So, again associativity is again what we have told is a very it is a closed door concept. If it is more associative, it is a more of a rich man's club like that. Okay. So, who I think we told in the first class only that physics people are the most closed type of people, okay, and publishing in a physics journal therefore will be difficult than publishing in a biology journal and publishing in a maths journal perhaps, okay, or becoming a hero, okay, or becoming Sattam's director, okay. Anyway, and if you go back to the technological networks, what we see, technological or biological networks, what we see, it is mainly disassociative, okay. Okay. Yeah, negative value means rich goes with poor. Okay. No, that minimum was not 0. I have shown that it can take the limit 0 and 1, but it can always go minus. Huh? Yeah. So, if it is, yeah, if very good, if it is negative, that means you can immediately find a rich man or a high good hub and you can connect the network, okay. So, this is, but see this value World Wide Web, among all these values just notice the value of World Wide Web, what it is showing, or this value, I just take this value, what is it? Yeah, so it is much less minus than all the other values. It is close to 0. Can you guess why this is happening? No, there is nothing random. There is nothing random about it. It is okay. So yeah. So what is happening? This is basically World Wide Web is basically a combination of social and technological network. So that's why technological component of it is pushing it towards negative, while social concept is pushing it towards positive. It is a very interesting study which we know. Okay. Okay. So our associativity concept ends here. Only one thing I want to say is associative and epidemics. So tell me, if it is more associative, is vaccination more difficult? Yes. Why? Because if a densely connected person or if a more connected person gets affected, immediately many popular people begins to okay, I write this as popular. So many popular people also begins to get affected. Okay. So but in a disassociative, what is happening? If a virus is spreading, if it goes to a bigger hub, then it comes to a smaller hub. Okay. So that smaller hub will have less power of dissemination, but here immediately many people will be there who will have huge power of dissemination. Okay. Okay. So this ends our class here, but next class we will again go back to node property. We first talked about node property, then graph property, and next class we go back to node properties and talk about centrality. Okay. So centrality will what we will discuss in the next class. Okay. Thanks.